All right. We have some friends online. Masha, can you hear me?
Hello, yes, I can.
How are you today?
Good. How are you?
Very well, thank you. I'd like to go ahead and start. We're 15 seconds to 1 o'clock. We're returning to solids NMR. We had a little sojourn and we're coming back to solid state NMR. See what you guys remember, okay? Remember the rotor? Okay. So what I want to talk about in this segment is some pulse sequence elements that will allow us to do more than just measure an FID. They have to be done during magic angle spinning because that's how we get the sharp lines. But if we want to run a 2D, we need recoupling, we need a pulse sequence element to move magnetization from a source spin to a target spin, right? So I want to look at what some of these pulse sequence elements look like. And honestly, given the constraints of time and so on, I'm not going to get deep on all of them. I'm going to go very deep on one, a little bit deep on two others, and then some of them I'll be very, very superficial. Does that mean I think those are stupid pulse sequences? No, do not misunderstand me. That is not what I mean by that. I'm going deep into the ones that I view as an educational, reasonable journey, okay? It doesn't mean that they're the most important pulse sequence. It's just I want to pick the ones that illustrate some elegant tools and other pulse sequences that might even work better. They might be what Eric Keeler tells you to use, and he's right, and I'm wrong. But I just want to talk about these ones because it shows you how to think about how to have it. Okay, so pulse sequences during magic angle spinning for magnetization transfer. And I'm going to start with the heteronuclear dipolar Hamilton. That's the transfer that we're going to try to accomplish. What's heteronuclear? It could be protons to carbon. That's like our building block. That's what everything in modern solids NMR pretty much is done, based off of. But you'll see that we get on to talking about other spin pairs that are not the same nucleus, phosphorus to carbon, nitrogen to carbon, etc. But we might start with proton to carbon. That's like a base. And it's complicated because the pulses will be time dependent. There always are. The MAS gives you time dependence. That's a lot. And actually, they're time dependent on the same time scale. Someplace between 1 and 200 kilograms. So we're going to start with a workhorse 1D sequence. And it has, hello. Oh, sorry. No, not at all. I decided to start right on time, but you're fine. So the workhorse sequence we're going to talk about first as being an example of heteronuclear transfer element or magic angle spinning experiments is got the acronym CPMAS, cross polarization, magic angle spinning. You'll see this acronym all over the place. And a simple cartoon of it here could be broken down into blocks where the first thing you do is just project with a 90 to get some magnetization that's orthogonal on your protons. Then you have a transfer element. This is what we're going to be talking about today. That's why the text is in red. Magnetization transfer from the protons to the carbon by means of simultaneous spin locks. That's what we're going to dig in on today, maybe today and tomorrow, because I need to leave time for your problem sessions and everything. Simultaneous spin locks, and I ask you, please note the ramp. That means, in practice, oftentimes one of those spin locks will be variable amplitude, and it could be complicated function, it could be simple function. But in the first analysis that I'll go through today, I'm pretending there's no ramp. I'm really simplifying this so we can just see how to apply Hamiltonian analysis when you have spatial variation, magic angle spinning, and spins, coupling elements, and the RF. How do you simplify this and really think about it? just to finish up this whole sequence, then the next thing that happens after those two simultaneous spin locks is that, as we'll see today or maybe tomorrow, they leave you with some nice X magnetization on your carbon channel. And you wanted to measure carbon in this sequence. So now you just need to let go of that spin lock and encode an FID, but you will do that during decoupling. So decoupling of the protons from the carbon, typically, but not always, by strong irradiation. So I thought we were doing MAS on our protons. So doesn't that decouple everything? Wasn't that the whole point of MAS? Well, it doesn't completely remove the homonuclear dipole couplings of the protons, a point that I will be returning to. So, but just now for the moment, be aware that when we want high resolution carbon spectroscopy, this is a good tool to get some magnetization on the carbon. And this, under most experimental conditions, is necessary. That also do more than just spin to get rid of the carbon proton couplings. And the problem isn't the carbon proton coupling itself, the problem is the proton coupling. So that's sort of the cartoon of the larger context, but as is typical for pulse sequence analysis, we're just going to zero in on this when we do our Hamiltonian analysis, because that's the new piece we're learning about today. Maybe we'll come back and talk about some other things, but this, I assume you understand that, the 90-degree pulse. So what we're talking about is just this element. So we start out assuming we have X magnetization on H, that's perfect, that there's nothing the matter with it, and we ask what will we have on carbon at the end of holding two spin locks. And what is it about those spin locks that we're going to have to be fussy about? I need to say a little bit of history before I dig in on the spin physics. I'm going to say more about some of these people on another slide, but the idea that two spin locks would be a good experiment came from Sen Hartman and Erwin Hahn in a paper in 1962. And that shows that what we're about to discuss actually works. They had the intuition, they had the observation, and they might not have used the exact same Hamiltonian tools we're talking about, but they understood. Then you jump to 10 years later, and Alex Hines, John Waugh, and a coworker, Gibby, used this whole sequence element together with magic angle spinning to look at carbon, natural abundance, and useful materials. And that was an all-in, like they were taking different tools from different literature precedents. So what I'm talking about today, they take the credit for doing the total experiment for the first time. But there are really important contributions independently from Jake Schaefer, especially as we move on to say, can we use that same approach now to move between nitrogen and carbon? Can you put two spin locks and move between any two channels? That's Jake showed that that's a good experiment, and finally, I want to mention in the Griffin group, when Mark Baldus was a postdoc there, they developed the idea that when we do the transfers between maybe a nitrogen and a carbon or some other rare spin pairs, that you could do that selectively, that you could move only carbonyl to nitrogen or only C alpha to nitrogen. And that could be really useful in assignment problems. And I mentioned this paper in particular, even though it's just a little tweak to the groundwork built before. But I mentioned it specifically because part of what I'm going to emphasize in my lecture follows that paper very closely. So if there's one paper in the literature that my lecture connects closely to, it would be this one. Okay? So on the left, the same whole sequence we already talked about. You excite some protons, you have two spin locks and move to the carbon, and then you detect that free induction decay with decoupling. On the right, it's a cartoon for double CP, this Schaefer experiment and the centerpiece of all this paper, where first I move from protons to nitrogen, and maybe I would measure the nitrogen chemical shift in an indirect dimension. And then I move from the nitrogen up to the carbon, and then I detect the carbon. So there are two CP steps. The first one being proton nitrogen, the second one being nitrogen carbon. That's what's discussed in the bulk of this paper, and that is therefore important for me to mention from the get-go, that it might not be only proton carbon, but it might be
The little tax income.
oh, I didn't get it. I just hit, okay, thanks. Thank you.
So since you knew Hockerman, did he ever say how they came up with the idea?
The next slide. I'm gonna come to that. Not the next slide, it's like a couple after that. So I mentioned that initially I wanted to focus on unlike spins, heteronuclear dipole coupling. So these kind of processes between like spins could be energy conserving, secular if you like, and they could be facile, and there could be lots of ways to accomplish them. So homonuclear transfer sequences behave a little differently, and there are lots of them, and some of them are governed by really clean physics, and some of them aren't. Nuclear sequences, I think there's more of a sense you need to have a game plan, like how are you handling this Hamiltonian? And that's part of the reason I'm picking it here, but we will come back to homonuclear because it's very important in the analysis of proteins and nucleic acids. Like we have to talk about it. I'm putting it off. It should be the easier one in practice, and it turns out to be the harder one in theory. So let's put it up. We're going to do heteronuclear, and again, another big picture comment before we dive in. So we were all good about the FID and how magic angle spinning helps that out, like and how to predict an FID. These transfer sequences, they're needed for lots of things. Say for solution. You have some low gamma rare spins, and many times they have super long T1 values. But they're actually interesting. They have more chemical shift dispersion. There's more information at them sometimes than the proton measurement. But you don't want to do a one pulse on those most of the time. You don't want to do a one pulse on those. So being able to transfer from the proton to that rare spin, at the factor of gamma, you're going to get more polarization. But that's not the big boost. The big boost is now you're going to be working off of something that you can wrap regularly because of the proton T1 being in a reasonable range, guaranteed for a biopolymer always. And the carbon or the nitrogen, most of the time being just horrible. So sensitization. And then that was the original motivation. And then transfer in multi-dimensional experiments. I just showed you that in the context of a pulse sequence. And also, we use these same pulse sequence elements to measure accurate distances or maybe torsion angles or close cousin of these sequences that we're going to be talking about will be used for shearing and anisotropy measurements. So they get used for fine structure to get constraints for structure calculation, that sort of thing. So they get used in so many different ways. Now, the first idea you might have, if you want to move magnetization from hydrogen to, say, a nitrogen or a carbon, well, what do we do in solution? We could probably do it in salts, right? Well, we were doing something like an inept, right? You might refocus it or some other things, but basically it was an inept element, right? Well, you can do that in magic angle spinning, and people do. And it will have the same requirement. What was the requirement to have a successful inept for solution? Chris knows that all my rhetorical questions are answered on the slide, and it's fair game. Go for it. I do the same thing in the other class. I just like type the answer, just so you can read it. Just like to see if you're awake.
That something with the chemical shift difference compared to the coupling strength.
We're gonna have to compare the coupling strength to something. What would we like to compare it to? All of these sequences work in a transverse plane. Like, you're gonna have a lot more to work with once you put the spin down in the XY plane. You've got J evolving and all that. So what's the governor of whether it's gonna work or not once you have the spin down in the XY plane? Who's our enemy?
Realization.
The relaxation in the transverse plane. So how about these values for a solid? J is going to be of the order 90 hertz on an NH group, 150 hertz on a CH group. What is the transverse relaxation rate that we're fighting? Well, optimistically, it's really fast. It might be north of 100 hertz. It might be 200 hertz. It might look Lorentzian, but there's a lot underneath that. Like it's not like omega squared tau ski. It's not like another R2. There's all this spin diffusion and craziness going on, but basically it looks pretty Lorentzian and it's like, more than 100 hertz probably for any of the hardware we have here, a lot more than 100, unless you like get rid of all the protons in deuterate or something else. Okay, so that's not good. That's not good. It's going to barely work. And it does barely work, and people have demonstrated it. But is that really the best thing we can do? So enough sequence would work somewhat, but what about an analogous experiment where instead of using J, you use the dipole couple? How about that? Can we do that? What do you think? What opportunities, what complexity might come up if we decide to do that? What could be good about it? The answer is non-existent. Why might we like the dipole coupling better?
Just information about how close they are in space.
It's space. Actually, Kurt Berger told me I was retarded to do this. The dipole couplings. I can't remember if he said that in public or in private. Are you using the same interaction for your through bond and your through space McDermott? That's my favorite imitation. Actually, no, it's more like that too. Like skiing while he yells at you. It's true what you said, and it's not broadly viewed as an advantage. So what else?
Since we're talking about it after the previous limit, I assume it's just like stronger.
Much stronger. Much stronger. So let's look at that. So we're fighting the same T2 presumably, but if you add 2 protons at 1 angstrom, which is, they're not quite that close when they're general, but it's like 120 kilo. If you have NH, north of 10, CN bond north of a kilohertz, and C alpha similar, DC. So this is great. This is like, we're okay with respect to our typical T2 all of a sudden. What might be complicated about it? That's what's good about it. What might be complicated about it? Yes, please. CHY, because I'm talking about aromatic versus aliphatic. And actually, it should be 150. It just should be arranged here on J if you want to see like I brought that up. What about what could be bad about this or complicated? Anything come to mind? Yeah, that's complicated. I mean, it might be good. I don't know. We're going to have to worry about this. So, dipole couplings are much larger, but if it's static, it's literally a function of theta, the angle relating B naught to the dipole vector. For liquids, what are you going to get for the dipole coupling? 0.0 unless you align them. For MAS, what will we get? What's their time average? For the dipole coupling under magic angle thing, and I've been reading some of Malcolm's papers over again, papers I read a long time ago, the beautiful papers, but every time he shows for the specific case that you actually set the angle correctly.
Well,
No, that's like Twitter. It's like.
I was told once that David Neuhauser and Malcolm Levitt, it's a big argument over whether you could have a phase-sensitive nosy spectrum. And Malcolm kept saying no, and David, it was very practical in our spectroscopy, said, I can look at my spectrum and they're clearly phase-sensitive. And finally Malcolm said, let me see the pulse sequence. And he looks at this, oh, you mean for the special case of a nosy with 90-degree pulses.
It is the same thing, right?
I asked Malcolm, he denied ever saying that.
Okay, anyway, if you're really at the magic angle, what's our dipole coupling average? I'm gonna spin nice and fast, do dipole coupling goes to,
Go to 0.
yes, thank you. It goes to 0, it doesn't have any terms that are retained. Okay, so remember this classical expression, these complex spatial dependencies, the fact that we use spherical harmonics, we reviewed the fact that this is the Cartesian representation, 1, 1 minus 2, which corresponds to a prefactor determined by the distance and the choice of gamma, which we have up there. And it looks like I dot S minus 3 I Z S C. So in the principal axis frame, you'd have 1, 1, 1 for I dot S, and then you minus 3 I Z S C. So this is how dipole coupling looks. Very, very much orientation dependent. It's a classic uniaxial interaction, and it is traceless, is the important part. Traceless, so it averages to 0. We also solved expressions using the Euler angles for the dependence on spinning, and that'll be on a later slide, but we used expressions like this to get those. So we know that it's time varying, we know it's sinusoidal, we remember that it had a cos omega R piece and a cos 2 omega R piece. Oh, here they are on this slide. So there's a displacement from the isotropic shift, has a cos omega R piece and a cos 2 omega R piece. And these are just projection factors for the dipole strength. Delta, which again is a function of force of nucleus, gamma, and 1 over R cubed. And that oscillates and absolutely averages to 0. So now there's a problem. Now there's a problem. So here's a plot of the rotor angle and a plot of the coupling strength, which we looked at before when we were deriving just the FID equations. And starting at time 0, and then at the end of 1 rotor period, at the end of 2 rotor periods. And coupling itself is crossing 0. 0 is here. This is the magic angle. It's crossing 0 exactly when it hits the magic angle. So it's averaging to 0. So I'm not feeling very hopeful here. I think whatever you develop with that dipole coupling, you're going to end up at another moment in the rotor cycle when the coupling changes sign, and then you refocus. It's like putting pi pulses. It's the same intuitive picture that if you change the sign of the coupling, not by using a Hahn echo in this case, but by actually moving the sample, it literally changes the size and sign of the coupling. It's probably just going to refocus. So we need to worry about that. So if we spin fast, we understand it would be 0, but now it's looking like even if I spin slowly, it's kind of complicated, but it's not going to do that. So it averages to 0 during MAS or liquid, so why am I wasting your time on it? Here's the thing that underlies the rest of this lecture. what if at certain moments, every rotor cycle, like maybe here and here, here and here, I could hit one of the two spins with a pi pulse. So just when the rotor in a spatial degrees of freedom was about to flip the sign on my dipole coupling, I say, ah, not so fast. I'm going to flip it here in spin space. It would come up and then it would go like that. And it would always stay below zero. Comes around here and I flip it and like that. So I could sort of rectify it by just swatting it with a pi pulse every time I see it's about to. Now you say, oh, wait a minute, that's a specific crystallite. You can't really stay on top of it for every crystallite. That's probably not going to work. Different gamma values, different beta values. Okay, but what about a sequence where I just place some pi pulses? Let's just figure out what's going to happen. I have a sequence and I place some pi pulses, and it's a good result. So pi trains normally, if I wasn't spinning, those would be echoes, and those would remove not just chemical shift, but heteronuclear coupling as well. MAS by itself, with no pi pulses, removes the net effect of your dipole coupling. Each one of those is an eraser for dipole couplings. But the fun, the magic here is that if I apply them simultaneously and synchronously, I bring it back. I bring it back. It does work. Such a pulse sequence in the context of the total sequence, just in case you would like to see this, looks like this. You have, did I animate this? I can't remember if I animated it. Yeah, I did. You have a prep. In this case, the sequence that we're really going to study today is just in the box at prep. So I'm trying to get some magnetization down on carbon. That's my apartment on cross-polarization. Then I'm here in the X direction for carbon. And what I'm doing here is I'm spending some time on the X-axis. I use a pi pulse in the middle of this period to refocus any chemical shift that might be going on. So I'm just sitting there in the XY plane, mainly along X. And coupling to the nitrogen would have been ineffective due to magic angle spinning. But it was shown by Jake Schaefer a long time ago, inspired by a previous EPR experiment, that if he would just hit it with a series of pi pulses, it would restore that coupling. And therefore, during this period, no net chemical shift evolution, but evolution under the influence of the CN coupling. It's a brilliant sequence and a very simple and elegant. So that's 1989, Jake Schaefer and Terry Gullion. And many years later, Chris Juraniak and Bob Griffin worked on some improvements for this family of sequences that really help their effectiveness in extensively labeled biopolymers. So those are two important references. But I mentioned this pulse sequence not because it's the thing we're going to do today, but because I think it's the most intuitive of them. That if you just hit it with 2 pi pulses per rotor period, you could like flip over every time it's trying to go and change sign on you. You can change sign back so that it restores the sign. Yes, please.
If you're decoupling the hydrogen.
Yeah, thank you. That's the part I forgot to say. So that was the pi train to dephase under the influence of the dipole coupling. Up here, you have decoupling by just strong irradiation of protons, assuming it's moderate to low frequency spinning, old school rotors. This I did mention is a pi pulse just to make sure there's no chemical shift going on for the carbon. And this represents the FID that you're actually detecting the remaining magnetization on the carbon after you leave it in contact with the nitrogen for a while.
Right, but if you're decoupling the hydrogen, like, are you refocusing? before then.
Why doesn't the decoupling bring back the CH coupling, kind of like these pi pulses are? That's a really, really good question. And actually, I think people in the field didn't talk about that enough for many years. And then there was a paper, sorry, I don't remember the first author. I'll tell you later. Where they pointed out this possibility, what you just said. And they left us with an idea of a best practice, that decoupling needs to be either way weak compared to the MAS or really strong compared to the MAS, but should never be about the same. So let's say your MAS is 20 kilohertz. You should be way above 40 kilohertz, preferably above 80 kilohertz, honestly. Or down around 1 or 2 kilohertz, like a solution decoupling sequence it would be. That's an excellent question. So we're going to talk more about the importance of being on the same time scale as this lecture goes on. Okay, so finally, so I said this grew out, this whole sequence that we're going to focus on here, where you have the two spin locks. Now we're going to start to dig in on it and understand why it's working. So we talked about this high pulse train only because it's a little bit more intuitive for the first glance. People feel comfortable with it, even if there's no Hamiltonian to go with it. But now I want to talk about a pulse sequence we use every day that works differently than that because it's based on the spin locks, so the CPMAS. And for this one, we're going to dig in with some formal Hamiltonian treatment. And it comes from the famous experiment where Sven Hartmann, as a student in Erwin Hahn's lab at UC Berkeley in early 1960s. It's a real classic method. So it had been not that many years, less than a decade, that Robbie at Columbia University and Erwin had been here at that time. He'd been in the physics department and then the IBM Watson labs when Robbie had done this mutation experiment. It was like a molecular beam experiment, but hidden inside of the very first magnetic resonance experiment, arguably. It was another guy doing EPR in Russia, a guy called Savoytsky, but those were the earliest experiments. And Hahn would have been, aware of that and set up his lab at Berkeley based on these ideas, and was thinking a lot about these Rabi frequencies. In other words, not the Larmor frequency, but the precession from, or the movement from Z to minus Z and back up, these frequencies, would they be an opportunity to move magnetization between unlike spins? You have a carbon and a hydrogen, and they can never match their Larmor frequencies. There's no field that they will match. They're always a multiplicative factor of Bohr. And you can't get a field inhomogeneity big enough to bring them into. That will never work, and he was aware of this. But because he thought a lot about the Rabi experiment, he was aware that this other frequency, the Rabi frequency, is an opportunity. It's an opportunity to access other physics. And so he became interested in the question, what would happen if for a directly bonded pair, a hydrogen and a carbon, for example, what if I matched their Rabi, not their Larmor? Wouldn't that also connect the two dipole together and therefore create an opportunity for transfer of information or polarization or magnetization? So it was an intuitive inspiration from Hahn. Now this is the same person who first did the echo. So clearly he had a vision for manipulating Hamiltonians, that we don't need to just take what we're served, that you can be clever with pulses to erase things and reintroduce things. So that was the original idea. And an analogous idea was then pushed forward. This is Sven Hartmann. And he was in our physics department until about 10 years ago. He was emeritus and then passed. This is Erwin Hahn, an excellent amateur violist. And this is Robbie. Sven Hartman, in his program here in physics at Columbia, thought about analogous experiments for laser, for optical experiments. It was a very big idea, a very flexible idea, just like the echo is, matching nutation frequencies instead of matching normal frequencies. Does that make sense? Just as an intuitive concept? I don't know if that's quite enough of an answer for your question, Art, but that's just the way that I understood it. So, like the high pulse train from Jake Schaefer, this cross polarization could be used as a heteronuclear magnetization transfer during magic angle spinning, and it's overall more popular. They each have advantages and disadvantages, and sometimes I think we should be using the pi train more often than we are, but I would say if you look at the literature, you see more of these CPs and double CPs. So it's a big one to understand. It's complex for the simple reason that it has time dependence, sample orientation, and time dependent pulses. So pulse sequences during magic angle spinning can be analyzed best using an interaction frame. And a tool that we're going to talk a lot about today called the effective Hamiltonian. So that's what we're doing today. In order to use this as a exemplar, I'm going to idealize a lot of things. A lot of things that really matter in practice in your experiments are going to just go away because I said so. So it's the two coupled spins that are otherwise totally isolated. Nobody else is bothering them. And that could be because you decoupled so well, it could be because you were very good with your isotopes, something. Also, it's going to be totally static, no motion on anything for them. Now, the actual Hamiltonian has a lot of pieces. This is the problem. In addition to the time dependence, it's the complexity of the Hamiltonian. It is chemical shift on the one you want to detect. Oh, I'm sorry, I'm using I for being the source spin. I just said it better. Chemical shift on the one it's coming from, for the moment proton. Chemical shift on the carbon that you want to detect. Dipole coupling between two different protons. Dipole coupling between a proton and a directly bonded carbon. That's what we want. There's like a gold nugget in the middle of a bunch of half here. This is the RF irradiation that we can pick whatever we want there. So that's the tool and the RF on the S. So we get to choose those two. The rest are given to us by nature. And we want to use this one. And we have to put up with everything else. So I could rewrite that being a little more detailed about the functional forms that we know about, and also just turning it into a frequency because we're used to reading it that way, and product operators. So it's delta omega for I, and that's the IZ operator for the chemical shift. Delta omega for S, so the offset, and then that's the Z operator for chemical shift for S. Dipole-dipole couplings. I just reminded you that this is how they look. But sometimes you just see the IZSC, and sometimes you see this whole thing, I dot I and IZSC. Why is that? How come half the time when we put up a couple of Hamiltonian, we just say IZSC, and then sometimes we have this whole thing that I have there. I'm going to use this whole thing. It's not, it's going to matter that I have a whole thing in a later step. So let's just stop for a minute and say, why did I do that? I justified it on an earlier slide by reminding you that we did it over here, possible. But how come we're just like randomly using the one we want that day? Sometimes it's just IZSD, sometimes it's like.
I think you justified it with like dipolar coupling not in the Z direction was not small.
It's small or big, doesn't make it effective or ineffective. Sometimes small things really matter in NMR Hamiltonian, but there is something ineffective about it sometimes. The Z and the Y pieces.
To make a singular approximation.
Yeah, and what does that mean?
Only the transforming with
Mm-hmm.
Z
And when can we make that?
when Z component is much larger than the other X or Y components.
But you also, need to think about for these two spins, are they, almost degenerate or not? If they're almost degenerate, they're on the same nucleus, and this coupling is so strong compared to the chemical shift difference. Old literature, we would call them AA prime spin systems instead of AX spin systems, right next to each other, so that their tails are even overlapping or worse. Then that secular approximation is over. Then transfer of energy between I1 and I2 is isoenergetic, and we should not be making that approximation. So for protons and solids, never stick, never stick. You don't use IDSC. If somebody does that, you just stop right there. If it's a heteronuclear Hamiltonian, we do this in solids the same as you do in solution. Okay, is that okay with everybody? All right, so those are the pieces of the Hamiltonian where we talk about all of them. So here's the heteronuclear. So I cut it off to IZS. Okay. Now, I already said I want to work with this. Oh wait, where is my heteronuclear? Yeah, IZSC. And then I pointed at this and said some nonsense. This is RF on spin I and RF on spin S. Okay? So this is the only piece I'm trying to get anything out. This is the guy. Okay? This is my tool to erase all of this somehow. And so since this is what I'm interested in, let's remind ourselves that we know what the prefactor is. And also we know that by the end of the problem, we're going to have to put this time dependence in it. This thing is a function of time. Just reminding you that here, but I don't want to put it all in one equation or just go 1 or 3 1. So for this thing, we have to sub out the time dependence. So 2 spins, INS. You have to worry about homonuclear dipole couplings and the heteronuclear that we want. If I leave out the homonuclear, it's just not very accurate. Chemical shift on each spin, irradiation of both, magic angle spinning. And what am I trying to do with this Hamiltonian? I want to assume an initial magnetization, like I said, is X magnetization on the protons. And I want to predict the density matrix at later. I was a little self-contradictory because on the previous slide I said I'm going to oversimplify, and then I put this back in, HH coupling. So maybe that's a little schizophrenia on my part in terms of like, we need to leave it in, can we take it out? But I have an interesting argument about why it goes away or when it goes away that might relate to your question, Chris. So it's good I'll have to do it. That's a lot of terms, most of which we wish were 0. So your first instinct should be, can we jump in a different frame? Can we go into a different frame and see this more clearly? So we want to simplify that long string of Hamiltonian terms to use an interaction frame, sometimes called a toggling frame, because we're going to treat the RF pulses, each one of them. Toggling refers to the idea that sometimes it's more than one pulse. Then you have one for each spin, and each of those in a more complicated sequence could be in blocks. So it might be worse than non-inertial. It might have discontinuities and so on, but we have to follow everything the RF is doing. I call that a toggling frame. The analogy is to the rotating frame. Remember that the transform frame is related to the original frame, laboratory frame, by a fictitious field A equal and opposite to the Zeeman term. And we use a transformation U, which is a rotation, it is conserving amplitude, but it's non-inertial. The laws are expected to look different, and we're lucky if they're analogous and recognizable. So here, you transform with a different fictitious field, not A, but A prime, that is equal and opposite to the RF pulse. And then we'll pick the RF pulse that's helpful. We want the eraser of choice here. The interaction frame generally introduces something equal and opposite to anything you'd like to buck out. This transformation starts in a doubly rotating frame, meaning rotating frame for I and rotating frame for S. For the proton and the carbon, we're already in the rotating frame. Now we want to be in a doubly toggling. So we're going to remove both RFs. This idea of
Yeah, just a warning to people. In the literature, solution NMR, doubly rotating frame frequently means that first you rotate around Z, and then you rotate around omega I.
that here, I'm just calling it toggling frame. That's a frame that follows the RF. Doubly means two channels in most of the solid state literature.
So it's so much different usage.
And I'm just pointing out down here, and it may have been said already, that these kind of frame transformations, that's the difference between what we talk about with the Schrödinger and the Heisenberg representation. So two ways to draw any quantum mechanical dynamics equation, choice of frame. Are you leaving all the terms explicitly in, or are you jumping in a frame where they seem to have gone away? Net action of both RF fields and both of the static offset fields. In other words, I first went into the rotating frame, so that removed isotropic shift, the way that we like to do it for solids. We remove the isotropic shift and we remove both RF fields. That's the job of you, the frame transformation. Okay. And pseudo force is introduced. And this is just a reminder that if you sample at the completion of appropriate RF cycles, there is a very simple relationship between the interaction frame and the original frame. So we're going to solve what it looks like in the interaction frame. But sometimes it's not easy, or you don't want to for some reason. And you are guaranteed that at the end of each cycle, the two frames will join. Then you can just do synchronous sampling, stroboscopic sampling. So one frame, one channel, sorry. So one transformation for one channel is A is the equal and opposite to the actual RF field. Both channels, it's the total A, I guess I was calling it A prime on an earlier slide, but the fictitious field is the sum of two RF. Now, this term is going to act only on the I degrees of freedom. This term is acting only on the S degrees of freedom. So it's not too complicated to write them and do them in one step. Just act on S with the S1, I on the I1. These are heteronuclear, they don't overlap at all. And what do these transformations look like? Well, let's do one explicitly in the Cartesian basis set. So chemical shift, delta omega Iz, a chemical shift term for I, is going to be viewed after the fictitious field, which is written where here. Well, anyway, it's the I rotation around the RF. So it's this piece here. So here's the original Hamiltonian, Iz Hamiltonian. And if you had a little offset in the rotating frame. And then if you apply an S spin, it does nothing. So you just put a unit operator to account for the S spin. So that's a rotation around the S spin and do nothing. And then you rotate around minus X for the fictitious field, with the argument of these sinusoids being the omega 1 for the I rotation. And that is an X or minus X type rotation. And so you compute all that out, it's pretty simple. And you'll get this expression, which is quite intuitive that you're having a cosine modulation of the original interaction, the Z interaction. So if you have an offset, it'll look like that offset. And according to cosine omega t, and then because you've been rotating around X, you'll get a Y length piece according to sine omega t. So it's just what finger physics would have told you. You're rotating around a fictitious field of the equal and opposite of an X pulse, and it turns a Z-type operator into Z-type operator cosine omega t, and a Y-type operator sine omega t. You can do this with all the Hamiltonian pieces. I picked an easy case and went back to the Cartesian expression to do it. And here's a question: would you like at this stage of the problem to have instead done it with spherical harmonics, which would have made you more comfortable? If you want as a study example for your exam to redo what I just did with spherical harmonics. The thing is, part of the reason I did it the way I did it, it's just an easy case, so you can do it either way. Also, it's like a L equals one object, and we didn't spend that much time on L equals one, but more working with L equals two. But you could do it as a study problem. It wouldn't help rate course. Does that make sense as a question? Okay. Now we have this whole menu of interactions in the rotating frame. We might have an offset. I was saying, you know, a good rotating frame, we wouldn't even have this. I'm going to need these terms, so I worked with them. If you did have an offset, like you could say, well, my rotating frame can't be on resonance for all my carbonyls. It could only be on resonance for some of them, right? So let's work it out. Let's have this at the ready. Homonuclear dipolar coupling. We talked a lot about why that looks this way. Heteronuclear coupling, spin lock field, spin lock field. Each one of these, we can rotate that set of spin operators around X and see what we get, okay? So I only did these two for you, and they're pretty easy. Is everybody comfortable with the first two lines, with what I'm saying, what I'm planning, and how I got it? Might be laboring this too much for some of you, getting bored. You good? Yeah. Okay. So when I come down to these, again, I only need to tend to the I pulse because this is a purely I operator, but I need to rotate everything around that. So a ZZ becomes a ZZ, but it picks up two factors of cos omega 1. And when it's not ZZ, it's YY with a factor of sine squared omega 1. Now what happens to I J dot IK when I rotate it? What does that look like? What does IJ dot IK, the I dot phi operator look like as being something to rotate?
Interval should be variance of rotation.
Yes, thank you, invariant. So I did just write it down again. So if I have ones on the diagonal and I try rotating that, not so much happen. But the IZ becomes sinusoidal variation between Z operators and Y operators. That's an important one. This one is also important, but much easier. So I have to rotate IZ due to the I pulse and SC due to the S pulse. I do those separately, and I end up with 4 combinations. I would say this line of everything on this compact table is the best one for you to take to review your notes from today and make sure you agree that there are no typos here. This is the heart of what we're trying to do here today. And you should understand this one transformation without any confusion. You should be totally confident. So if you look at this and you can't derive it, you should bring it to me or Art or Anish. Now, if by design, if I jump into the frame with the fictitious field that's equal and opposite to the spin lock field, I want to see that thing go away. That's what happens with B naught in a rotating frame. Okay, so these are zeros. This has a time average of 0. This has a time average of 0. Doing so bad. We go into this frame and we've gotten rid of 1, 2, 3, 4 terms. I'm happy. This is happiness. We have two, dipole couplers. And crazy thing about it is that they're both deeply time dependent. And we have to put those together with some spatial dependence. This omega here is also time dependent. So we're having sines times sines. So it's not simple, but at least we only have the two terms. Okay. Everybody okay with the big picture thumbnail sketch slide? I've left you with one piece to confirm, but besides that, I feel like I walked you through most of it. Questions? Anyone? So what we saw there is some terms are invisible or zero in this frame by design. Whatever we use for the fictitious field, we erased it fully and completely. Others become time dependent. And actually, those are the ones that don't commute with the fictitious field. Those are the ones that become time dependent. Many of them also become zero in the average. Like I pointed out one in the last slide. Because this is just a subsine and sine variation, we know that if we take that interval, we'll get zero. So that time average is zero. So some become zero by design, some become zero in the average. So are we satisfied that that really means that they're zeroed out completely and we don't care about them? We need to make a time-independent approximation for that time-dependent cyclic term. So that's a time-dependent Hamiltonian. We are interested not in the Hamiltonian itself, as beautiful as it is. We actually want to study the net action that it has on the spin system. And is that net action really zero? And we want to be careful about that. So we're going to look at a method to take these time-dependent Hamiltonians, that, and satisfy ourselves whether they really do nothing to the spin. So up till now, I've worked intuitively with you, acting like, looks like it averages to zero, like the reader. And now we're going to look at a tool that is used in the literature, in the NMR literature, to be more careful about that. So we have a time dependency with the term. You have a whole bunch of them. What you want to do is approximate them with a time independent approximation. Something where you don't see time in there, but it looks like over a cycle, it would have the same net action on the spin system. The expansion of preference here is a Magnus expansion for this interaction frame expression. And the first leading term in it does turn out to be the simple average, like what I've been saying, use your intuition to take the average. So this is an expansion, and the first term in the expansion will be the time average. Now notice that I didn't put the MAS in yet. That's going to come. Yeah, so we see an effective Hamiltonian, meaning the effect is the same. Time independent, whose net action, the rotation, the exponent, is the same as the original time dependent Hamiltonian, but you don't have all this crazy time dependence. It's effectively true, or an approximation close enough. Is not necessarily the same as a simple time average. Not necessarily a rotor cycle average. Why not? Let's think about an example. Choose an initial state being a spin vector along Y. Although average Hamiltonians do not need to refer to an initial state. They should be true no matter what the state is. But let's just pick a state to be concrete so we're all thinking on the same problem. You're sitting on Y and you do Z pulses of an arbitrary angle, and then you do a minus Z of the same equal length. What happens? Does somebody say nothing? Yeah. And are you sure of that? You wind it and unwind it. That worked. So we can just average it, right? What if I do a Y pulse and a minus Y pulse on a Y vector? Nothing. That's really doubly nothing, right? What happens if I average a Z and nothing? I know I can average that. Just divide by time. So all of these are fine. We can just average it. Now, consider the average of a Z pulse and then an X pulse. Z and then X. You start with Y, and then I want you to do a Z and then an X. And I would prefer if you just use a 90, so we're all doing the same problem, because it turns out that a small angle is a special case and a 180 is. So let's just do a 9. Okay. By the way, this actually represents something we care about. Z might be a chemical shift in your Hamiltonian, and X might be a dipole interaction in your Hamiltonian. Excellent. Okay, so if you have these two, and it could be that in part of the rotor cycle, you're real active on the chemical shift, and then you rotate, and now you're real active on the dipole. So one operates then the other, then one and the other. This is realistic kind of thing that comes up in MAS. Okay, so what happens if you do Z then X? What happened to your impulse? Start with Y.
First, let's even X and then one negative X.
Hmm.
Afterwards. Negative.
Wait, if you're sitting on X after the Z, negative X, and now you do an X pulse, what happens? Nothing. So does that look like the average of the two terms? No, we have a good graph example where one of them's got erased. So what would you say in general? You can average them when they all commute. But if you have two terms that do not commute, and they may be varying during the rotor cycle, sequenced in different ways, it's called the Dyson time ordering operator. You sequence them in various ways and they don't commute. Good luck. That's not an averaging problem. Okay, so in that case, not necessarily the time average, this difference is important if various terms with various time variations do not commute. So actually the smart thing to do is to expand, to choose an expansion, which is an expansion in commutators. That way we're pretty safe that we know we can truncate it quickly when the commutators are zero. We know that this will have the truncation properties that we want. The Magnus expansion is just such a thing. It's a time-independent approximation for the time-dependent terms. The effective Hamiltonian is a series where the first element in the series is just a simple average. The second one is a correction if the Hamiltonian at one time does not commute with itself later. It's not self-commutating over the cycle. And if that doesn't clean it up, then you might need to take a triple commutator and so on. That's what these terms look like. This was used for NMR, I believe, first by Hegel and Lenoir in 1968. And watch out because sometimes the nomenclature is different where people call this H0 and this H1 and this H2, but I follow this convention, which is also elsewhere in the literature. This is the first order term. These are so-called higher order terms. For strong RF, CW applied fields in comparison with the coupling strengths. The first term is much larger than any subsequent fields. Do you see why that is? If the RF is strong compared to the interactions, it will converge. The series converges nicely, even if the terms don't commute. Why is that? What's this integrating up to? When do we stop the integral? Do we have to take it out to infinity, or what are we doing here? This is a strictly cyclic Hamiltonian. And remember, I was saying you even know that it joins the frames at the ends of cycles. So you are integrating these dummy variables finally up to the end of one cycle. This is not an MAS cycle in this case, it's the RF cycle for the fictitious field of the RF. And at the end of that cycle, how far have we gone? Well, not very far. If the RF is really strong, that's a short cycle time compared to evolution. So you're just moving your R naught just a little bit. That's a good convergent limit. It always is. Small angle could be convergent. In other words, you're going to gang up copies of tau C, and tau C is a small number. This will be like tau C squared, tau C cubed, and that's helping you truncate. Okay, it's small compared to the interaction. Now, yeah, it just says the answer to the question there. Each subsequent term could be different in terms of which pieces of the Hamiltonian show up, and you do get those factors of 1/2 or 1/6 or whatever, but it is really the fact that the time is short or strong RF. Now, what kind of an expansion is this? Let's look at what we're dealing with here in the kind of big picture. So we could have used a Taylor expansion. They're both approximating time-dependent solutions in lots of contexts, not just NMR. The Magnus expansion solves this general problem in a form that looks an awful lot like a rotation, and in fact, a guaranteed unitary. It preserves probability. It contains nested exponential commutators, which efficiently handle what we need here. The Taylor expansion expands it in a much more familiar way. So we could be on familiar territory, we could feel more comfortable. It can violate unitarity at any finite order. And because you're using a power series, it can become more complicated than a commutator. So for this particular problem, there could be a strong preference for the Magnus. Now they are related. Well, you could take the Magnus expansion if you wanted and expand it using a Taylor series. And there you'll get another famous series. And you can also derive the Magnus expansion starting from that series. So there's connections, but you don't get the Magnus out of the Taylor. That wouldn't work. And a lot of this is explored in a nice paper, which I think is part of somebody's PhD thesis. Who is Magnus? German-American mathematician, American because World War II. So he's a really important person at the beginning of algebra. He refused to join the Nazi party, and so he got kicked out. He came to NYU, the Courant Institute, and sort of stayed there for most of his career. And I want to mention that he has a very famous student who is at Barnard, Joan Berman, who worked on related problems, and is still somewhat active as an emeritus in her 90s. Okay, so it truncates to the first term pretty effectively if RF is strong enough. We're going to do the first order analysis today. And I was just thinking about selecting a problem where we go to second order, maybe for next. So when that doesn't converge, you need those higher order terms. People talk about them all the time when their whole sequence doesn't work. They say it's due to higher order terms. Okay, so some terms will be invisible or zero in the interaction frame by construction. Others are time dependent, and that's where we need the effective Hamiltonian, and we will use this Magnus expansion. Still others are non-zero because they commute with the initial spin state. That's a different reason why they don't evolve. And our job is to find the RF that works to make everything go away except the specific one. Reminding you. Okay. So which term are we dealing with here? We are going to deal with the homonuclear dipolar coupling. Okay, and we're applying a spin lock to it. And this is your question, Chris. So you start out with rho naught is IX because we wanted that IX there because that's what we're going to transfer over to the other spin. This term commutes with the effective homonuclear Hamiltonian. So here's the Hamiltonian, IZ, IY, I dot I, right? We got these by rotating IZ around IX, with that frame transformation, and we got this. And we could start to say, what's the time average of it? Turns out it's not going to go to zero, so we're not going anywhere good with that. We could come back to this problem and do a proper Magnus treatment. But what I'm gonna say right now is to notice that the whole Hamiltonian commutes with the initial magnetization. So absent cross terms, we're not gonna have any evolution anyway. In practice, though, you are right that unfortunate dipole coupling strengths and magic angle spinning do lead to making sort of like strongly active homonuclear couplings. So this doesn't work at moderate spinning frequencies in practice. This is an interesting approximation for early times. The problem with it is that we don't just have two spins, we have a network of spins. And we have other terms that take it away from pure IX. So we do need to take the Magnus expansion to higher order for this problem. But it's not going to be the one I pick to do with you because it's an unusually messy one. This is just an argument that initial descent, the initial evolution of that starting state, rho dot is zero because it commutes. So for that excuse, I'm going to ignore it. All right, so we're saying what? This first order Magnus is zero. I'm sorry, this first order Magnus is zero. For these, they are literally zero by construction. And we just argued that this one commutes with our initial magnetization, so we'll ignore it. It is not averaging to zero. And it is not totally inactive, but we're invoking that excuse to ignore it for now. So now we want to look at it. This is a frame transformation where we have isolated one term as being active and all the rest of them as being obliterated by one way or another. Now, before we treat that term, we're going to transform it with a trick. So this is time average. It's the first step. So we have cos squared omega t. Do you happen to remember what the average of that is? The average of cosine omega t is 0. The average of cosine squared omega t. Have you ever thought about that or needed that for another problem? This is like a rectifier. You take a cosine function and multiply it by another cosine function. And now you have something that's always positive. So it's not going to average to 0, right? So our heteronuclear and homonuclear will both be subject to terms like that, like cross terms, cosine, sine, or cos. So for this homonuclear coupling, the time average of cos squared and sine squared is one of the things we need, and it happens to be 1/2. It's just the answer to that. You can solve it on your own time. So we get a Hamiltonian that looks like 3/2 IZSC, 3/2 IZ, sorry, and then IY minus that. And I'm going to use the thing called the magic zero, which is that we know that if I take 3 IZ minus I dot I, and then we rotate that to the other two orthogonal directions. So 3 IY minus I dot I, 3 IX minus I. If we add all three of these up, we get 0. That's called the magic zero. So you take a full, not truncated dipole coupling. If you can spend equal time where it's along Z, and then you have a frame transformation where it's along X, and then you have another frame transformation where you park it on Y, and you get equal time to those three situations, the first order, you've gotten rid of it. And this is used in a lot of pulse sequences. Here, I'm just using it as a piece of math, but in other pulse sequences, it's used really to remove homonuclear couplings. It's a very cute thing. So because of this, I can substitute out for this expression. You just use this to rearrange it, and you can see that it's equivalent to 3/2 IX minus I. Just rewriting that. Nothing else. And that helps you see that the initial magnetization really commutes with that effective union. The use of that magic zero. So short times it will not evolve. This is a first order analysis. It's really not valid unless your deuterated are spinning really fast. And keep in mind that geminal protons are at least about 40 kilohertz, but they're not even isolated. They sit within a quasi-infinite coupled network with final or tertiary neighbors, which all have couplings around 7 kilohertz. So within a half rotor period of 5 to 50 microseconds, you've touched lots of things. You're out into the network. And eventually you find something that has a legit REX term on it, and the whole thing is very dissipative. The network picture, which we call the band, or relaxation sinks in the band. And all this funny behavior of the protons has a tendency to also broaden every carbon in the system. So this is an important phenomenon. So I'm making an argument here on the one hand saying, yeah, that commutes with the initial rho naught, and so let's ignore it. And I'm also admitting at the same time, it's not a great approximation. And it remains our biggest foe to actually make that come true, and not just here. All right, so I've said enough about this term. Now we're ignoring it, ignoring this. The one specific wanted term, heteronuclear dipole, is this. It takes this form and it has 4 terms. You are going to, as your review for today, you're going to verify this, see if you find an error. Any pair of field strengths for which the average is non-zero. So we get to pick omega 1 for I, and we get to pick omega 1 for S. We get to pick these, okay? So any pair for which the time average is non-zero is referred to as a matching condition. And a matching condition means that the interaction during that pulse sequence, if it involves magic angle spinning or not, or whatever, if I choose those 2 values so that this averages out to be non-zero, we call that recoupling, the opposite of decoupling. For example, if 2 field strengths are selected to be equal and there's no magic angle spinning, then I'll get a sine squared type term here and a cosine squared type term here. So I'll have something that survives at a time average over the omega 1 omega 1 cycles for both spins. Okay. So any pair here that I can choose, and again, what's under my control is omega 1I and omega 1S. Any pair that I pick where the time average is non-zero, we refer to as recoupling. And this is really interesting when you do it during MAS. I'm pointing out that the average heteronuclear dipolar coupling does not commute with the heteronuclear . The effective average . There's a typo here. I'm just saying that this initial magnetization does not commute with the effective average. So you're going to see evolution there, and that's what we want to study. We just fix that line here if I can. Initial magnetization. Okay. So we have an initial magnetization, first order term for the Hamiltonian, and we have evolution we're interested in. We've really simplified things down to a problem that we can do. Now, in general, these kinds of problems, even though you can write it in a nice little closed form and we just have the one term, they still can be tricky. You want to predict the density matrix at later time, you can only crank it through numerically, but that's not what we want here for this kind of a example problem. So we're going to use a trick called the Baker's-Hausdorff-Campbell expression. Did you see that already? These names sound familiar to you? Yeah. So here's a special case. When you have a pair of a Hamiltonian and a density matrix for the initial state, they do not commute with each other. So you know there's evolution. Special case is if you take their commutator, you get something or other. Now you take that and take a second commutator with respect to H. And that might look familiar to you from previous lectures. So I take the commutator to find out what the derivative is. Where am I going? Is sort of what the inner one here asks. And then wherever I'm going to, what happens if I apply the Hamiltonian again on it? The special case, if that returns the original density matrix times some constant. That's a special case in dynamics. It doesn't happen all the time. If that's the case, you have a cyclic oscillation between your original magnetization that you started with and this funny thing that you make after one application of the Hamiltonian, like the initial descent, whatever that thing was. Like, say this is Ix, this might be Iy if the Hamiltonian is Ic. So you have Ix, you make a little Iy, and once you make Iy, you return the Hamiltonian on it, and you come back to Ix. So this is like oscillating between Ix and Iy under an IC type operator. So you're in a special space where there's only three things: where you started, what you're going to evolve to, and a Hamiltonian itself, and they operate cyclically, and you get this kind of a prism. So if you want to know if your problem is that easy, you take your initial density matrix, you take two commutators with H naught, and you say, oh, this is dead easy. This is just like Ix, Iy, Ic. You can derive this using a Taylor series. And I have a slide here about that, and I'm not going to read it to you. I'm going to encourage you to look at it. And it's not that tedious, and you can work it through and come to us with a question. It's very, very useful thing to be aware of, that double commutator. So I have a couple of slides here in the deck that help you guide you through the derivation of Baker's, Hausdorff, Campbell. And I think it's what I want to skip from today in interest of time. Now, I want to point out that there's a different special case, and this comes up just as often as the classic one. Let's say that your double commutator does not return your original. Then you're like, oh, nonsense. Oh, nuts. I can't even do this problem. You're not done yet. You're not done yet. You should take one more commutator. So this would be like a triple commutator. I don't know why I wrote it this way. For some reason, I take the first commutator R1 and then I take two more. So I'm up to R3, okay? R1 is just this regular thing that we do every day. R2, you take the resultant of that and one more commutator. R3, you take the resultant of that and one more commutator. Sometimes this doesn't work. But then R3 is some omega squared times R1. That's like, it's not cyclic initially, but then it falls into a cyclic pattern in the subsequent steps. That's almost as useful. I'm sorry because this green goes right through this. But if that's the case, then you have a dynamical equation that looks like this. At later times, it's the initial, with no time dependence on it. It just sits there in the equation. And then the R1 term, your first term here, will appear sinusoidally, and the R2 term appears as a cosine function with this added -1. And then you don't have to put a term for R3 because R3 is the same as R1. And you don't have to put a term for R4 because R4 is the same as R2. So you end up with this pulling these sines and cosines out of the Taylor expansion. So being aware of those two possibilities, that either the double commutator will return the original density matrix, or if that's not true, one more step pulls you into a cyclic pattern. You can solve many simple problems in time dependent. Okay, so I just summarized what I said here on this slide. So this is a summary to check your problems if they have a trivial solution. The problem we were working on. Here's our Hamiltonian, our initial state. And here's the evolution. Because it turns out this is the second type where if I do the double commutator, I do not return this, but if I do the triple commutator, I return the single commutator. So then I can use this expression. And that is a very good description of the first early time behavior of a Hartmann-Hahn cross-polarization experiment. You begin on whatever you were on, and then sinusoidally, you develop some SX. So that's your protons, and that's your carbon. And one more term here is funny. It's not necessarily observable. It's like an antiphase, something or other. Or I'm sorry, a double or zero quantum, something or other. So you're going between IX and SX, and sometimes in a hidden type coherence. Okay, that's what the Baker's housed up Campbell tells you. This I think I would choose for my stopping point so that there be a little bit of time for problems. Yeah. So we've gotten to where we see an expression for the evolution of magnetization getting moved from proton X to carbon X because we had two spin locks. And it is a function of the dipole coupling. We've removed the RF. We've removed other couplings, other chemical shifts, just evolving under its own dipole coupling. And there will be moments when you get maximal magnetization on the X and minimal on the protons after 180 degrees. And there will be moments when you have everything in an invisible state. That might be useful or not, might just be annoying. Let me just tell you, I encourage you to look over this a little bit tonight. I circled one problem for you to work on. What are we going to talk about tomorrow? We're going to talk about a slightly better experiment in the sense that I'm going to include chemical shift offset a little bit more, and by using a tilted frame. But the most important thing is not that. The most important thing is that I'm going to put a magic angle spinning in, which I didn't yet, and talk about where we want to put omega 1 and omega s. Are we matching them like we did in this problem? They had to be matched in order to get rid of that and get the maximal effective dipole coupling. With magic angle spinning, maybe that's the right matching condition and maybe not. So we're going to find out. Okay. So the CPMAs, we haven't done the MAS part yet. So that's where we start tonight. Any comments, any questions? Yeah.
Can you go back?
I'll just go slowly. You tell me when to stop. I think you want the proof of the Baker's.
Yeah, so
That one?
like this special case where you have like the double commutator, and then you have this omega square.
Mm-hmm.
I'm thinking the omega square is like forward rotation.
The frequency, characteristic frequency of the experiment. And whatever this product gives you as a scaling on R0 will turn out to be the characteristic frequency of the problem. And usually it's a number you've seen before, like omega 1 or something like that.
Okay. Yeah.
So here, Just remember, in this problem, we apply a matching condition, and for this problem, without the MAS, the best matching condition is just to say that these two fields are equal, right? That's where that came in. So in that case, you'll have a factor of a half being the average of sine omega 1t. So that makes this go away. So these two terms will survive. And the factor of a half from this and the factor of 2 that's formal that's out front will cancel each other. So you just have IZSC plus IYS. So this is our Hamiltonian on this slide. This is an important slide. Applying a matching condition. And really the job tomorrow is to ask what kind of matching condition should we have? We have to throw magic angle spinning in on top of all of this so that we get narrow peaks. Make sense?
So these frequencies are different.
Yeah, this is your B1 dictating the Rabi frequency. We're assuming we're on resonance, so there's nothing funny about it. One. So the gammas are not equal. So to get nitrogen to move as fast as hydrogen, you need to put pulse. Like there's your kilowatt amplifiers, where proton you should not be using more than, I don't know, 10, 20 watts. Right? You need to really kick the nitrogen so it can move as fast as the proton.
Yes. Where do we? So I guess I understand this matching condition here for the macronuclear coupling,
Yeah.
but is the reason why the homonuclear coupling during the spin lock went away? Is it also because there was a matching condition, or is that always going to happen?
Let's see, this is where it was still time dependent. Homonuclear, right? And then this was after the time average. So it's just like self-matching because the two protons always have the same RF, so it's self-matching, right? And so you always end up preserving some under this family of pulse sequences. So I didn't make it go away. The pulse sequence did not make the homonuclear coupling go away. The best I could say is that if I rewrite it, the trick I wanted you to be aware of for other benefits that it has, I rewrote it using this thing called the magic zero. It's really easy to see that this could commute with the original. So I'm saying it doesn't really evolve that much if the cycle time is short. And the spin system is simple. Both of which are falsehoods, but whatever. So that commutes, so let's pretend nothing happens with it. But I didn't make it go away, it is self-matching.
And then wait, isn't it for the when you say cycle time, that's like the Rabi.
Yes, it's the only time dependence we have so far, because I didn't put any MAS in.
Oh,
So cycle time here is always B1. Mhm. It's the only frame transformation, the only physical time dependence we've had. And the next step is to put the MAS back in. But the way we cast the problem, we've set ourselves up so that it's not so bad. It's not so bad.
then why did you say this only works for time approximations? Like, is it because once it starts relaxing? Like, basically an eigenvalue.
Mhm. Right, right. So this problem in particular. Couple things about it. One is that the bad actors here are geminal protons with couplings of 40 kilohertz. And so we should not be using small angle approximation anyway, because a half or a quarter of a rotor cycle is not short. A half or a quarter of the B1 cycle is not short. And what about your question? But the B1 cycle and the magic angle are on the same order of magnitude. How do we know that they don't act as a rectifier or bridging spec? Like, there's all sorts of worries with what we've done here, and we don't have the MAS there yet. So let's just talk about the B1. It is not a really short cycle compared to a geminal proton coupling. That's horrible. Okay, the second thing is that it is not an isolated spin pair. That isn't even true. I made some approximations at the beginning that both the heterotron would be treated as an isolated spin pair, and if I put the HOMO in at all, it'll be an isolated spin. These are falsehoods. So, the fact that you have more than one Hamiltonian term, maybe a chemical shift, but definitely another dipole coupling, you make some moves that are finally unrecoverable in the second half of the rotor cycle. And you don't even need to invoke motion or anything stochastic. It just doesn't completely unwind. It's an old problem in solid state NMR that's intrigued very, very good people. And it's just not a very convergent problem. It doesn't resolve well, other than brute force. Just simplify your spins. Just do it. It's an infinite network where, in order to say that our cycle times really are short compared to the strongest couplings, we need to be spinning at 500 kilohertz. So we get very excited about going from 100 to 150. I get excited. I think it's super cool. But actually, it's not where we need to be either. And the same thing for the RF. We love to go from 100 kilohertz to 200 kilohertz. But the reality is that it's still not the small angle approximation. Okay, it'll all converge when we're around. And then, so we're not close to that. We're not close to that. So what we should probably be doing to solve actual problems today is either have a new breakthrough in the whole concept of a full sequence, which I don't know what that would be, but I imagine it's out there someplace to be had, or just do great. Just do great.
What's the problem with slowing down?
What's that?
You said you could either be really fast in comparison,
Right, which would be like a half a billion.
or you could be really slow.
Oh, in order to not reintroduce a coupling, you could be much slower than the coupling and do something clever with the spinning side. Yes, that's true. But then you run into a different aspect that is the part of it that has, I think, been intriguing to people and has remains more unsolved than solved, which is that we're dealing with a quasi-infinite bath of protons. And our intuition and our formal expressions all come from isolated spin pairs. And do they really recouple? And where do you leave reversibility? So you have 1, 2, 3, maybe all that recouples 4. But when you go to many, when you go to Avogadro's number, it behaves dissipated. And why? What's happening there? But you lose into the larger network of spins, things that don't fully recouple in the second half of the rotor cycle, if you think about the slow spinning limit. And understanding that, the first thing you notice when you get into simulations or read papers about simulations is that it's extremely topology dependent. You have these really weird end effects where magnetization kind of gathers up at the ends or bounces back. It's complex dynamics in the extreme. And so that's why I say I hold out hope that there's something clever and something general in it. But I haven't seen it.
So in your derivation, you started with X magnetization and the RF pulse was also in the X. Does there need to be that relationship between the initial RF pulse and the RF pulse derivative?
For this theory. Absolutely. There are experiments we do that don't have that geometry, and they operate differently, and they're not always that much worse in practice. But this family of experiments is intended to be done that way. Like there's one, I don't know if we'll have time to talk about it, a legal group sequence. It's a little bit different in geometry, but the way that the Hartman non-cross polarization is meant to be done is exactly what we just. Other questions, other thoughts? Okay, we take a short break and then we do some prompts. Anish, are you on the Zoom?
Yes.
I'll stay on for a little while just to make sure I'll, before I take my stuff off. I wanted to talk to you about a controlled experiment. It may not be our top priority right now. This is in that category of if we end up with unusable machine time or whatever, you know. This is like, it could be any field. I'll just describe it. It's, great questions today. So, do you know how the way you approaching T1 experiments, you sort of begin with explicit concern about polluting by spin, homonuclear spin diffusion, right? And we came up with some controls and whatever. I was thinking kind of big picture about the on-one-row experiment. I think we're getting close to actually writing our paper and doing the final fitting and everything. And I realized we never did the corresponding for that. In other words, carbon solution. Also, I know I thought of this question early on, and I thought of the same approach to say, well, with that spin diffusion, I should be able to use it as a mixing sequence in a 2D, which may underestimate the artifact. But if you see it, now you're morally obliged to act on it, right?
Yeah.
But we never did it. I think there were just so many exciting things going on, and we just never did it. So sometime when we have ACSA, and it could be a contrast in the way that you set it up for the T1, that there's a uniform carbon in places. And then there's the sparse carbon that we usually use for all of them. Everybody's 2 minutes. You know, for a typical, so I was just talking to Eric about it. Sometimes, yeah, the time that I don't think it's our top priority. Because if we see bad news, then the whole world will come apart.
Yes.
I don't want this. Maybe one control many times. I'm sorry. But you know what I mean, right? You get the picture.
You know, the class that you were not teaching Friday, my God, was I know him telling us very thoroughly. Do as many controls as you can, or somebody else will. That is in trouble.
We have to eventually, but maybe not when we're running a group. That would be bad timing. Okay, do you need anything?
No, I think this is. What?
This is like your phone.
What's it called? I haven't uploaded it yet. Is that what you mean?
Okay, sorry.
Yeah, that's okay, geeks.
Oh.
What is it?
It's,
Hydrogen and a carbon
yeah, Harvard.
and a sugar.
Science.
Uh-huh. Do you use the sugars as replacements for us?
Sometimes. See. Both time. Or.
I think people online can I think
And usually they're pretty for that. So we.
this will work. It will work.
Values.
Problem. I mean, probably it's.
That's funny. Well, everything
Solids.
Okay, so today's session, in the time that we have, I'm going to talk about a subject that we did have time to go over in the last problem session that we dedicated to solid state NMR. And this is in connection to the last homework that we have to turn in for solids, and specifically the last problem on that problem set. This is the problem as a reference. So the problem text says, calculate the fast limit tensor for the carbon in an aromatic group, assuming a uniaxial tensor of the static case, with the ring perpendicular being the unique axis, delta, sorry, delta by data, with delta, and two side flipping motion. Then it says do the same thing for a carbon in a T-butyl group with a fast limit three side motion, assuming the static tensor for each methyl carbon is also a uniaxial CSA. So this problem, and right above this, we have this particular formula. That m fast is 1 over n, sum over I equals 1 to n. The rotation matrix is applied to m in the PAS way. That's what this formula is saying. I'm going to take a minute to put my phone on my laptop on charge.
Will you look at your
I have mine. Okay. Let's start by the first part of the problem, which most of the classes did get right, and then we'll try and sort of get some thoughts about how to approach the second part. So the first part of the problem is describing to you an aromatic group, and it's asking you to focus on, say, a particular C13 in that aromatic group. If I consider the CSA tensor of this carbon, CSA tensor, according to the problem's description, where is the z-axis of this tensor? Start with, is it in plane or out of plane? Out of plane. So that's the z-axis. Because it says the ring perpendicular is the unique axis. So the z-axis, kind of like that, going into the screen. If I assume that the tensor is unique, uniaxial, where are the x and y? Axes of the CSA tensor. Right, so in the plane of the base indeed. And does it matter where? How? Does it matter along CH? At an angle to CH? Does it matter? If the tensor is uniaxial. No, it does not matter. So if the tensor is uniaxial, for the special case that it is uniaxial, which it is far from, I can assume that this is my x-axis, this is the y-axis. Is it uniaxial in reality for an aromat? Not quite. And if it is not, does anybody know where the x and y axis will land? Well, the z is the unique axis is always perpendicular to the ring, and that means the x and y will still be in the plane. But will they be any two perpendicular lines on the plate. When I said uniaxial, I could as well have chosen this. Thing is, it doesn't matter if the tensor is uniaxial. But if the tensor is not uniaxial, can I do that? You can't. So it turns out that the x-axis, if I remember this correct, the x-axis lands along the CH bond, and then y-axis is perpendicular to the x and y. That's where the aromat CSA tensor, which is far from uniaxial, closer to eta equals 1, will actually land up. But for now, I'll come to the non-uniaxial case in a minute. For now, let's assume that you have this uniaxial CSA tensor, and you are attempting to rotate the molecule by 180 degrees in this manner. And this is a phenomenon that has been documented in proteins for two-side flip between landing and spring, for example. In terms of Euler angles, how would you describe this rotation? Or the CSA tensor? This uniaxial CSA tensor with axis described in this manner.
180 degrees, so that's your y.
Around x or y indeed. And if we follow this convention of, well, for any rotation has to be described by three Euler angles. Right? So what are all three Euler angles? Alpha, beta, and gamma.
Beta 180 and the others is 0.
0. So 0, 180, 0. The Euler angle for that rotation, or the set of Euler angles for that rotation. And 180 around y is the choice that I make to stick to the ZYZ convention. That's important just for consistency across how we describe rotation. We stick to the ZYZ convention, alpha, beta, gamma. Alpha and gamma rotations around z-axis, beta is rotation from y-axis. So do we all see that this is a 0, 180, 0 rotation? I'm going to step back for a minute and I'm going to tackle a slightly more difficult case. What I'm going to do for that is I'm going to assume a general rotation 0, beta, 0. I'm going to apply this on uniaxial CSA. Now, the logic is simple. You could do this, of course, also using spherical harmonics. I'm going to do this with the Cartesian. You can go back and review this state calculation using spherical harmonics. But what I'm going to do is I'm going to take the CSA principal axis system and rotate it through these Euler angles using the appropriate rotation matrices to arrive at a rotated tensor. So the CSA is given by breadth delta. What does it look like in its PAS system in Cartesian? Well, let me assume uniaxial to start with, and I get this. If I only have one set of one rotation around around y through an angle beta, how do I represent the rotation matrix?
Cosine theta.
Yeah. Because I'm doing R inverse and R over here. I get a minus sign here, and I'll get a plus sign here. Does this make sense? So this is rotation around y through an angle beta. And as you can see, this is the term that will stay 1 because y rotated around y does not do anything. And if you rotate x around y, you get moves towards minus z. And z rotate around y goes towards plus x. So if you take those considerations, you get this rotation matrix. Does this make sense? Now all you have to do is calculate the multiplying tensor. Right? So let me take these two first. What does that give me? Anybody? Term by term, what the matrix will look like.
Negative tensor routine. This
This is going to take over.
Yeah. Negative tensor routine.
And this is just sticking out one term for each row of the second matrix. What is that going to be? Minus delta sine beta 0 delta cos beta. That right? Okay. Then you do the final matrix multiplication. So this is this followed by this for example, and then you go through that term by term. That's minus delta over 2 of squared beta. This is a pretty big matrix. It's tough because there's a lot of multiplication going on. As usual, because you have a rotation around y, the y term will always remain invariant. If I understand this correctly, you will get here minus 3 delta over 2 sine beta cos delta. I just did that by going through this term by term. So the first term is this with that, and this with that. Does that make sense? Then you have these zeros all around because of the structure of the matrices that you started with. And then the next one is this, that, this term, this term. You walk through that term by term and you get this matrix. First question is, you rotated the matrix to an angle beta around the y-axis. For this rotated matrix, is the original PAS still the PAS for this rotated matrix? The question is asking you about what happens when you average, but take a step before that and ask, you had a tensor which was in its principal axis system and you had a diagonal tensor in that principal axis system. Then you rotated it around the y-axis through an angle beta. Is that rotated tensor in this axis system? Is this axis system still the principal axis system for the rotated tensor?
Well, because it's off that.
Yeah. There's no diagonal terms. So the axis system that was the principal axis system for the original tensor is not the PAS for this rotated tensor. Does this make sense? So you've got this situation where, let's say you've got like carbonyl group. I'm trying to represent the plane of the carbonyl perpendicular to the screen. So the z-axis is in the screen. And you have got a conformational fluctuation, which is causing this carbonyl to bend in this manner. Plane of the carbonyl is bending through an angle beta. That means that in its two geometries that the carbonyl group is in, the CSA tensor in the two geometries of the molecule does not have the same principal axis. Does it make sense? Slightly different. You could guess intuitively that given this geometry, you have a common y-axis, right? Because that is the axis through which you're actually doing the rotation. You have a common y-axis. And in each case, you could individually define an x-axis. So if the molecule was doing this fast enough, when I'll talk in a minute about what fast enough means, where do you think the average principal axis system will look like? Just this.
Yeah, it's like where your original part.
And so does the other orientation not matter at all? Let's say the molecule was doing 50% of the time in this orientation and 50% of the time at this angle. And it was doing it really fast, and I'll talk about what fast means. But does the other orientation not matter? Will it just be this?
It's the average, right? So it's just like the normal principal axis system.
Well, the z will land along the bisector.
Yeah.
Does that not make sense?
Yeah, which is like the original.
Like the original.
Yeah, so you're saying there's two principal axis systems, right?
For the two conformations that you read. Yes.
Okay.
That's kind of how I'm describing this problem, in the sense of saying the molecule is rapidly exchanging between these two conformations. Two conformations don't have the same. And remember, of course, when you describe all of this, all of this is being defined. Where is being defined relative, for example, to B naught. So you have a molecule with a certain orientation of the z relative to B naught, and that is again given by your powder angles, which show up in a static average of frequency or the MAS. But now I'm adding further complexity by saying that molecule which has a certain orientation, the orientation relative to P naught, which defines the molecule fixed frame. But in the molecule fixed frame, this particular functional group itself is undergoing conformational fluctuation. And so in that molecular fixed frame, you had two arrangements for the principal axis system. If you're rapidly exchanging between the two, the average principal axis will land along, for example, the bisector. Now, then, if it's true, if this fluctuation is fast enough relative to what?
And Gaussian difference between the two sides.
Right. So in this case, there is no change in isotropic chemistry. So this will anisotropy. So the exchange rate is sufficiently greater than the tensor anisotropy. That becomes the condition for approaching the first limit, the mostly averaged chemical shift tensor. In this case, of course, you have for every crystallite, and by crystallite we mean for every Euler angle for the molecule fixed frame, you can calculate what that fluctuation, what this orientation and that orientation will look like. That's going to change for every molecule fixed frame. And then you arrive at this. Yes.
I think you just implied something I want to explore a little bit more. So if we're in a fast exchange, you can't change the trace of a tensor by averaging it in two breaks. You can't change the trace by rotating it, so you can't change it by, these are linear operations.
Yeah.
That's exactly right. But if you were in intermediate exchange, you get these funny line shapes, so all bets are off. I think you just implied that, but you didn't put a fine point on it. Is that right?
Yeah, yeah.
Is that what you meant? I agree with you. It's not a point that gets really emphasized in the literature that much. Partly because if that were your scenario, intermediate exchange, funny business, whatever, you would have a weak line anyway.
Yeah.
But you could have no actual change in isotropic shift that you would kind of expect. You might effectively look like you have that data. Have you seen any reference to that, or did you just think of that?
Well, it's isotropic shift.
Apparent change because intermediate exchange. Did you see that somewhere in the literature, or did you just imply it into it?
No, I can't say I see.
Yeah. Well, with the cryoprobe, you might see such a thing.
Possible. Possible. Yeah.
We have to simulate to see that it's
Yeah.
interesting.
Yeah. Yeah. I mean, yeah, for intermediate exchange, final answer will always be simulation. Fast exchange, we can do these analytical calculations which tell us what the average tensor, for example, will look like. Will appear like once you're in fast exchange, once you are sufficiently fast, that is an order of magnitude faster ish, and beyond that range, you just have the average tensor. You can keep increasing the rate constant and not see any change. Yes.
What about fast exchange for the aeronaut? You take the mean critical access system, it doesn't make any sense.
It does, and I'll talk about that. So, for example, for an arbitrary angle, rotation angle data, we arrived at this rotated tensor, right? So I had the original tensor, which was in its principal axis system. In the same axis system, arrived at this tensor, which is off diagonal. So now, how do I calculate the average tensor?
If you just add that to the principal axis.
Well, so I just do this, which is the original tensor, plus the rotated tensor. If I do this addition, will I still have off-diagonal terms? I will, right? Then the average tensor is still not in its principal axis system. Then what do I do to land it in the principal axis system of the average tensor? Matrix has off-diagonal elements and you want to get rid of them. Diagonalization. Calculate the eigenvalues of the matrix and its eigenvectors will tell you where the principal axis system of the average tensor is, for example. So let me see if I have a special case that is interesting enough that we can talk about. Otherwise, diagonalizing with arbitrary beta is not a valid. Okay. What does this give us for beta equals pi, which is the case that we have discussed above? Right. So the tensor is unchanged as a consequence, which everybody can get correctly. The problem is that because these, when beta equals pi, this term and this term both disappear. And when they both disappear, you get back the original tensor. And that's essentially what this is saying. Like, you rotate if a tensor has its unique axis perpendicular to the ring, you rotate the ring around by 180, you don't do anything to the tensor. Does this make sense? Sort of like developing intuition for what is happening. Because the z is still parallel to where it was originally. You rotate the z around by 180. Therefore, nothing happens to the NMR frequency. And the tensor is still in its principal axis, still nothing has changed. Now consider the CH dipole coupling. This unique axis of the dipole tensor is along the internuclear vector. That's kind of like this. Do you think it will still be unaffected? Well, for the rotation, that is the flip of the phenylalanine ring. In that case, you have to think about what the Euler angle for that rotation is. Because now the z-axis is in plane and is along the CH chord. So if this were the z-axis for the dipolar tensor, and it's uniaxial, right? So then what is the most convenient pick for the y-axis? Is my question making sense? I guess it is not. Because I think I'm mixing up two tensors and it's getting.
So you're doing z is now around the CH line.
For the dipole tensor,
Okay.
for the dipole coupling, the carbon proton dipole coupling, the unique axis is along the internuclear vector. So that lands along the CH bond. The ring, right? So then for that tensor, this becomes y. And this is really important when we study the effect that the same motion will have on different tensors. And using this, you can actually sort of work back out what the geometry of motion is. Because one tensor is unaffected, another is severely affected. Use this effect to figure out what the motion is. So for the CSA tensor, we said that the z is flipped by 180, so it's parallel to its original direction. So the CSA tensor suffers no averaging. The dipole tensor has its unique z-axis along the CH bond, and the y-axis is perpendicular to the plane. In that case, what is the Euler angle for the rotation? Yes.
It's like a 180.
What is beta? Beta is 0.
Rotating on.
Flipping it this way.
I have defined the axis however you did it. Right? I'm doing that. So I mean, in a protein, for example, we have the C gamma C beta bond. Flipping it around that, I'm defining that specifically. So there is like an ortho-meta para arrangement over here. So under those circumstances, what is beta for the rotation? Related. Close. Multiple of 60. So you think about where this CH1 lands when you rotate it.
Wait, why is that? Are you rotating the C into like where you're about to flip?
This is what's happening to the molecule, yeah, for example. But effectively, what rotation is it? If I define this as the Y, it's this, right? With another rotation 180 around C, for example, which can be alpha equals 180 or gamma equals 180. So what one? Does this make sense? This was less intuitive than I originally imagined. For the CSA, he said 0 pi 0, alpha, beta, and gamma for the CSA tensor. And we said the CSA ran something like that. This is X for uniaxial. I would assume the uniaxial. Even if it is not uniaxial, you can show that, and then we talk about that in a minute if we have time. You can show that actually the tensor is still unaffected by that rotation. But this is, and that is the C. Then for dipolar, where I've got this. This is the z-axis, and this is the y-axis, and it is the x-axis is of course mutually perpendicular. After the rotation, I am supposed to land something like this. What rotation is that? Two pi over three.
Negative pi.
All right, all right. And then for consistency's sake, you can define a pi rotation after that or before that. It does not matter. Does this make sense? Even though the molecule is doing this, a 180 rotation around the axis. For the unique axis of the CH dipolar tensor, it's a 120 rotation. And so will the dipolar tensor still remain the same? Based on this matrix, this rotated matrix? No, right? It will have off diagonal terms. And then you can add that to the original tensor and then calculate. So this gives you a lot of how should I say algebra to do going forward if you wanted to do this calculation completely. Let me see. We can do one specific case, and that specific case is beta equals 90. Leads to some interesting results. Although okay. I got rid of that. So beta equals 5. Tensor is unchanged. Then beta equals pi over 2. What does the rotated tensor look like?
Wait, should that be 4 pi over 3? Sorry.
4 pi. 5.
Is it rotating on 40 degrees, right?
third of 360.
Oh, you're doing this one.
Tens of rotation. Okay. For beta equals 90, this tensor is also simplified. What does it look like? So it's still diagonal. I've done this interesting thing where by rotating around by 90 degrees around y, obviously I've split x-axis and z-axis. Does this make sense? That's what a 90 rotation around y will do. This makes sense. Showing you the calculation is consistent with simple logic. Now, the question is, what does the average tensor do? For the average tensor, half where you started. Plus where you are. And what does this give us? What is the new XX term? Yes, so if you take this half inside, and we'll do that in a minute. This is delta over 2. This minus delta, and the ZZ term becomes, and you do what Chris has recommended. So what's happened here? Does this average tensor have the same principal axis system as what you started with? It's diagonal in the same system, but it doesn't quite have the same exact same axes. Where's the z-axis of this average tensor? Along where the y of the original tensor was. Is it a uniaxial tensor? It is uniaxial.
By the way, you already gave an example, but many two-side pops turn a uniaxial into something that looks non-uniaxial.
Yeah.
So that's special.
90 degrees is a special case.
Yeah, so you're gonna maybe study an octahedral complex or something? Is that been done?
Probably.
Like Christian Fourier or something like that? Pretty cute.
Yeah, I guess that's what we would have to do. Find a two-side hop through a 90 degree. And this is what you would land with. You have no, so the average asymmetry, this is how we represent that. What is the average anisotropy? Now you have to sort of rearrange this tensor into the familiar format. Because now you've got y along z, z along x, and x along x, if you will. E1, average. The tensor is average to 0? No, it doesn't average to 0. What's the average tensor? We started with delta. It is still a delta. With, remember, delta we defined as ZZ minus isotropic. Assume that this is a traceless tensor, so that this ZZ. Yes.
Is it half? Is it
Half with a negative sign. right? Mind is this is important. Certain motional property which has not only cut the tensor by half but also flipped the sign. Right? That's what this 50, 90 degree hop has done. So your tensor, if you were to take a spectrum, this is what your let's say the static case look like. What would the average case look like? Right. So that's going to look like much taller. I can't draw this to scale, but kind of like that. We've engineered that effect through motion. This is average. Have you had this in a molecule, for example, a static solid took it below freezing point or some temperature below which the motion is in the slow regime, and then you heat it up, motion is in the fast regime, and you can observe this average tensor to get zero, to get negative half, to flip the sign and cut it by a factor of half.
It's like a dumb question, but
Mhm.
is it like a continuous transformation? Like, is there a point and it's like an isotropic peak?
What does the intermediate regime look like as you heat up, as you increase the temperature? Yeah, it's a very interesting question. And we don't have time today to go into that subject.
Hopefully we will later.
Yes, yes. But one of the things that happens, well, for example, a work from a paper that I think Anne referenced earlier in this class, which is work done by Kurt Zilm and David Grant on a molecule called dimethyl sulfone. It's sort of emerged as a model molecule. Yeah. Doing this right. Oh no, but it's totally wrong. It's sulfone. In this case, the deuterated version. So for the two-side hop around this axis, and this is a different geometry. You have to remember this is kind of like that. So this is a different angle. You can, for example, calculate what the angle of the. In this case, the CSA tensor is right along the SP bonds. So if you were to take the same example as the phenylalanine ring again, what is beta of the rotation of DMS? If it were an ideal tetrahedron, it is not, but yeah, so the tetrahedron angle is what we get. And for this particular case, Kurzel and David Grant have actually increased the temperature in very specific steps, and you can see how at the turning points of the average tensor, which would be for this case here and here, you start to see horns emerge as you increase the temperature. And the truly intermediate regime is kind of thought of as blob-like character, but you can see these horns emerging at the turning points of the average tensor. Then once you heated it up enough, you see the full average tensor. No remnants of the low tensor. Okay, so that was just what we had enough time for. Right? The EM people waiting for us outside. Hope this was helpful and see you next time.
Thank you.
Thank you.